Hello again. I figured since there's no homework due this week that I could post a video of me working some problems on op amps and Thevenin equivalents, and that might be helpful for you. I got a couple op amp problems, a couple Thevenin problems. Right here I've just got a quick review on Thevenin. So you've got your network with two terminals. You can turn that into a voltage source in series with a current source. The voltage source Thevenin is just the open circuit voltage, so whatever voltage is between these 2 points on your network when there's no load. Thevenin is the equivalent resistance of the circuit looking in from the terminals. There's a couple ways you can calculate this. You could find the short circuit current, so that's where you short these terminals and find ISC between them, short them. Then you just divide Thevenin by ISC to get Thevenin. If you just have independent voltage and current sources in your network, then you could set them all to 0 and you might be able to simplify it just down to one resistor. That would be Thevenin then. If you have dependent sources, then you do the same thing. You set all your independent sources to 0, and then you apply a test voltage, call it V-test, and then measure I-test coming off of V-test. And then Thevenin would just be V-test over I-test. And so that would look like, we'll do it on this, just V-test. We also talked about Norton equivalents. They're just a source transformation of a Thevenin. You have I short circuit as your source in parallel with Thevenin. Okay. So the first problem I've got here is from 465 from the back of the book. It's just a really basic resistive network with this current source in here. And they want us to find the Thevenin equivalent across the couple terminals. So 4 kilo ohms. This one up here is 2 kilo ohms, and this one's 3 kilo ohms. And we have A and B here. So Thevenin is just the voltage across the 3 kilo ohm resistor. We can get this by finding the current through the 3 kilo ohm resistor. That's 75 milliamps times 4 kilo ohms. 3K plus 2K all over 3K plus 2K. This is just a pretty basic current divider equation. I combine these two and these in series for it. That turns out to be 33 milliamps. So the 3K is just 33 milliamps times 3 kilo ohms, which is 100 volts. Okay. We can find the Thevenin resistance by shorting these two terminals. So let me draw the circuit here. So we short out this resistor. Very good. Short out this resistor, so he just goes away. You want to find the current here. So that's just the current through the 2 kilo ohm resistor. it's just going to be another current divider. So DK equals short circuit. It's going to be 75 milliamps times 4K in parallel with 2K over 2K, which is just 50 milliamps. So our Thevenin's V7 of that. Is 100 volts over 50 milliamps, which is just 2 kilo ohms. I'll show you the other way to do this too. So let me see if I can do this with a different marker. Instead of finding the short circuit current, let's see if we can get it by just shorting out this, or setting this current source to 0. So 0 milliamps. This guy is 2K, 4K, and 3K. This is 0 milliamps. A 0 amp source is the same thing as an open, so we'll just get rid of that. And you can see we can just combine these in series and parallel. So our 7 would be 6K in parallel with 3K, right? Combine these two in series, 4K and 2K. And that is also 2 kilo ohms. Furthermore, we could get the Thevenin equivalent by just doing some source transformations and combining some resistors, and I'll show you that too over here. So redraw the circuit one more time. Let's see. 5 milliamps. Sorry, I was hoping these chalk markers would be an improvement, but they aren't giving me exactly what I wanted. 75 milliamps, 4K, 3K. Oh no, let's do 2K. 2K. 3K. Okay. And so we can do a source transformation on this. Turn that into 75 milliamps times 4 kilo ohms, which is 300 volts. Put the 4 kilo ohm in series with that, and just redraw the rest of the circuit. Okay. This is still 2K and 3K and 4K. You can combine these in series and then do another source transformation. So show you that. 300 volts over 6 kilo ohms. It's is 50 milliamps. And here we'd have a series combination of these two, so 6 kilo ohms in parallel with 3 kilo ohms. B, A. You can combine these two in series and do another source transformation. So we already know from this 6K in parallel with 3K is 2K. So if you wanted to just redraw that with just a 2K here, we'd have the Norman equivalent. We want Thevenin. So 50 milliamps times 2K equals 100 volts. This is 2K. And you see, we get the exact same values no matter what method we use. So, I suppose if you wanted to check a problem, you could redo it using a different method. Okay, so this is the second problem I came up with. This is the circuit from problem 437. I just stuck a terminal here and here, and figured it might be fun to calculate the Thevenin equivalent of this. So for Thevenin, it's just the voltage across the 6-ohm resistor. You can solve that pretty easily using mesh analysis. So I already have them labeled here, but called this loop 1, called this loop 2, and this loop 3. So for loop 1, you have 6I1 plus 1 times I1 minus I2 plus 3I2 minus I3 that equals 0. Simplify that down to 10I1 minus I2 minus 3I3 all equals 0. For loop 2, you get minus 230 volts plus 1 times I2 minus I1 plus 2 times I2 minus I3 plus 115 volts plus 4I2. That all equals 0. Notice how this voltage source, I have it negative in here because we're coming into a negative and entering through the positive. This one is positive because we're going the opposite way. The current is going the opposite way when we're looking at this one. So we simplify that equation down to minus I1 plus 7I2 minus 2I3 equals 115 volts. And then for loop 3, let's see, you have 3 times I3 minus I1. Let's see, plus 460 volts plus 5I3 minus 115 volts. It's minus in this one because the current is going the other way and we're looking at it from I3's perspective. Minus 115 plus 2 times I3 minus I2. That all equals 0. You simplify that and you get minus 3I1 minus 2I2 plus 10I3 plus 2I3 minus 10I3, yeah, sorry. 10I3 equals minus 345 volts. It's just a system of equations, so you can very easily turn it into a matrix. Plus 1, 3, 0, minus 1, 7, minus 2, 115, minus 3, minus 2, 10, and minus 345. And you can either plug that into MATLAB or you can do the linear algebra if you're really good at linear algebra. What's important is that we find I1, because then we can very easily get V6 ohm, which is what we were looking for in the first place. That turns out to be 6 ohm equals minus 10.6 amps. So Thevenin is minus 10.6 times 6 ohms. That is minus 63.6 volts. So we found V7N, we need to find R7N. The way I approached this was to just short out all these voltage sources and calculate it directly by simplifying the circuit. So if we redraw the circuit, those shorted, we get this. And all the resistor values are what you would expect. 6 ohms, and we get the same terminals on each end, A and B. I approached this by doing a Y to delta conversion on the centerpiece. Do that in a different color. Do that in yellow. So Y to delta. This is 3 ohms, 1 ohm, and 2 ohms. I had to look up the formula for this because I don't remember it off the top of my head. But when you're doing a Y to delta conversion, in the numerator of when you're calculating all of these, you have the sum of each of the resistors multiplied together. So I'll calculate that first. 1 times 3 plus 1 times 2 plus 2 times 3 equals 11 ohms squared. So the way you do that, where you go from here is you take the resistor opposite to the one you were calculating and you divide this by that. So for this one, it's 11 ohms squared over 2, it's 5.5 ohms. This one is 11 over 1, it's just 11. This one is 11 over 3, that is 3.67 ohms. So, if we redraw the circuit yet again, it's that. We get this one's leaking too. Switch to red. Okay, and this is the same as what it was, 5 ohms, 4 ohms. This is 3.67 calculated. This is 11. Let's see, 5.5 and 6. B and A. So you can see these two are in parallel, these two are in parallel. Once you combine them in parallel, you can combine them in series, a lot of them in series, and then you can combine that in parallel with this, in parallel with this. So I do that all in just one step here. So let's see, we gotta switch back to back. 6 in parallel with 5.5 in parallel with this combination. 4 in parallel with 3.67 plus 5 in parallel with 11. Plug that into a calculator and get 1.87 ohms. So if we redraw the whole thing, we get minus 63.6 volts and 1.87 ohms. You can see when we have just independent sources and resistors, this process is kind of tedious at best. I tried to do this using just source transformations, and it gets much more complicated. So yeah, for some of these, just shorting out your sources is easier than for others. Finding the short circuit current may be simpler. Okay, so last Thevenin problem, and we'll move on to op amps. I got a sweater because it's kind of cold. This is problem 476 from the back of the book. They don't quite draw it like this. They talk about you wiring an ammeter to measure the current through this 50 ohm resistor here. If you've ever used an ammeter, you know that you open the circuit and then you wire the ammeter in series with whatever component you're trying to measure the current that's going through. So I just put a little open here and put A and B here. I'm not going to go through the whole problem. I'm just going to calculate the Thevenin equivalent, and then I'll leave the rest up to you if you so desire to complete it. This one has a dependent current source, so we can't just short out all the sources and calculate the resistances directly when we calculate our Thevenin. But, I'll start by redrawing this so that I redrew it because it made a little bit more sense to me when I did so. Put my terminals A and B up here. The 50 ohm resistor here. You can sort of see from this that the 80 ohm here and the 40 ohm here are in parallel. They both just go straight from this node down to this node. Ohms. 40 ohms. You can see we have this 16 ohm resistor here. Ignoring this dependent current source for now, we can see we go from this node to the 16 ohm resistor to this source and then down to B. It's a bit messy. Ohms, 40 volts. Over here we have something similar, except we have this 114 ohm resistor instead of a voltage source. So basically the same thing. 14 ohms, then 6 ohms. And then if we factor this in now, you can see that it's just going between those two nodes, which are these two nodes on our circuit. Let's see, and it goes from this one. That's 10 I phi. It's drawn a little bit small, but I phi is the current going through the 50 ohm resistor here. So I phi. Over here we have 10. So when we're calculating V open circuit, these are just open. No current's going to be going through this 50 ohm resistor. I phi will be 0. This will be 0, so this will also be open. You probably already noticed that we can combine these two in parallel. So for open circuit, open, we have resistor there. The value of this resistor is 40 in parallel with 80. That is 26.67. 661. This is still A and this is still B. This is still 16, 96, 114 ohms. And this is 40 ohms. So let's see. For my calculations, I did a sort of voltage divider. It's kind of hard to see here, but if we move this set of two resistors over here, they're going to be in parallel with all these resistors, with just this one resistor here. And then if we combine these two with this guy, we'll just have a voltage divider between the 16 ohm resistor and whatever the value of that is. So I did that all in one step. Thevenin is 40 volts times 26.6767 in parallel with 96 plus 114 over that again, plus the 16 ohm resistor. Plug that into a calculator and you get 23.86 volts as your V Thevenin. For R Thevenin, I put a test voltage across those terminals. I'll redraw the circuit again. So V test I also short out this voltage source because a 0 volt source is just a short. That's why this 16 ohm resistor ends up going to this same ground node here, because we're going to end up doing nodal analysis later. 96 ohms over here, and then we have that dependent voltage source, current source. 10 IV. We have IV here. We also have I test going the other direction. So I combined these two in parallel. 26.67 in parallel with 16 is just 10. After that, I did nodal analysis. So I called this node VA. This one's B. This one's down too. These markers were bad investment. This node is B. So KCL at node A, VA minus V test of 50 ohms plus VA over 10 plus VA minus VB over the value of this resistor, which I didn't appear to have not written down. It's 96 ohms. 96 all equals 0. The common factor between all these is 2,400. It's 2,000. Yeah. When you multiply that out, you get 48 VA minus 48 V test plus 240 VA plus 25 VA minus 25 VB. If you simplify that, you will get 313 VA minus 25 VB equals 48 V-tests. For node B, the equation is VB minus VA over 96 96 plus 10 I test. You can see from this that IC and I test are going to be the same, just flipped. So if we flip this current source and just call this I test, we can get rid of the whole phi nonsense. Plus 10 I test plus VB over 114. 114. That'll equal 0. You can see current through this resistor is just VA minus V test all over 50 ohms. If we want the right direction, we do V test minus VA. So substitute that in here. 10 V test minus VA over 50. And then same thing here. Minus over 96. As it turns out, the common factor between all that is 9,120. That leaves us with some very unpleasant arithmetic. 95, so multiply the whole thing by 9,120. Get 95 VB minus 95 VA plus 1,824 V test minus 1,824 VA plus 80 VB equals 0. Simplify that, you get minus 1,919 VA plus 175 VB equals minus 1,824 V test. So if you solve these equations, you will get that we'll ignore VB because it's not really that important. VA is minus 5.47 V test. We know that our Thevenin is going to be V test over I test. You already have that one expression here, wrote it down here, for I test. It's just tests, and then we'll substitute this value in there, so turn into a plus 5.47 V test over 50 ohms. You can see all the V tests will cancel, so we'll get 50 ohms over 6.47, which turns out to be 7.73 ohms. So if we draw out the final network we'd get with these simplifications, we would have 23.86 volts and your 7.73 ohm resistor there. Okay, so just to review op amps real quick, they look like this. You've got your positive and your negative terminals. You have your source voltages V plus and V minus. I think the book uses VCC. Doesn't really matter that much. And you have your output voltage. V out equals some gain A times VP minus VN. We don't generally use this that much because we end up assuming these things for an ideal op amp. IP equals IN equals 0, so no current entering these, and VP is about equal to VN. We generally treat them as being equal. Of course, if they really were equal, V out would always be 0, so they're really equal, but A is on the order of like tens of thousands, so if they're really close to each other, then this difference times A will end up being something somewhat finite. Okay, first op amp problem. So we have this network, 5-volt source here, 6-volt source here. We're asked to find IL on this going through this load resistor here at the output of the op amp. You can see there's a voltage divider here, so V positive is just going to be 6 volts times 5 kilo ohms over the series combination of them, 15 kilo ohms. That is 2 volts. If we assume the op amp is ideal, which we usually do, then Vn is the same as Vp. 2 volts. We can very easily get the current through this 3 kilo ohm resistor, because since there's no current going in here, it's just Vn here, Vn minus negative 5 volts here, because the terminals on this are flipped. So I 3K equals minus 5 minus 2 over 6K over 3K. So that is minus 2.33 milliamps. From there, we know that the current going through this resistor is also I3K. Again, because there's no current going into the negative terminal of this op amp. So V out minus Vn is over 6K is I6K, which we just said is the same as I3K. If we solve that for V naught, we get equals 6K times minus 2.33 volts. That's 16 volts. So IL is just V naught over 8K, 16 over 8, it's just 2 milliamps. Nice and easy. Okay, so this is the second op amp problem I came up with. This is problem 5.11. I'm going to do part A. This is an inverting operational amplifier. We have a potentiometer here with this variable alpha that determines how much of the potentiometer is shorting us to ground. Part A asks us, alpha varies from 0.2 to 1. Part A asks us how much V out varies. So start by assuming the op amp is ideal. So Vp equals Vn, which both equals 0 because we're grounded here. Current through the 2 kilo ohm resistor here is just then Vg minus Vn over 2K. This is 0, so just Vg over 2K. Since no current is going into the negative terminal, the current to the 50 kilo ohm resistor is the same. 50K, 2K. Down here, I should mention, I have I2K going this way. I2K. So over here, I50K is going this way. We can do KCL at this potentiometer. I just gave the currents here some names. So I called this current I alpha. I call this one going up here into the output I delta. You can see that I50K equals I alpha plus I delta. Let's see. So if we do KVL, we can do KVL from here to here, because this point is basically ground, right? 0 volts. So do KVL around here. We get 50K times I50K plus alpha times R delta times I alpha equals 0. So I alpha equals minus 50K times I50K over alpha or delta. Let's see. Our delta is 100K. That's just the total value of this potentiometer. So we can cancel out with this 50K, just get 2 in the denominator. 50K over 2 alpha. Perfect. So we'll just plug that back into here and solve for I delta. I delta is I50K. I'm again skipping a step here, but When you subtract I alpha from this side over here, it'll be negative, but that negative will cancel with this negative, so it'll just be plus I 50k over 2 alpha. We can factor this. I 50k times 1 plus 1 over 2 alpha. We can do KVL again. So you see that we have a closed loop. If we go around here, you can say that V out equals minus I delta times this section of R delta plus I alpha times this section of R delta. That will be, write that out, V out equals I alpha times alpha R delta plus, or no, minus I delta times R delta times 1 minus alpha. If we just plug in what we've already solved for, we get minus I 50k over 2 alpha times alpha R delta minus I 50k times 1 plus 1 over 2 alpha times R delta. I'm going to switch to a different marker. This one's dying. Much better. Times 1 minus alpha. So cancel these. We can factor out the I50k's. So we get, I also skip another step here. I plug in this for I50k. So minus 40 millivolts over 2 kilo ohms times 100 kilo ohms for our delta times 1/2 from 1/2 here. Let's see. Plus 1 plus 1 over 2 alpha times 1 minus alpha. And then, let's see, you can just simplify this. So minus 2 volts times what we've already written. 1/2 plus 1 plus 1 over 2 alpha times 1 minus alpha. We can just plug in alpha straight into this at 0.2 and 1 to get answers. So 1 alpha equals 0.2. V out is minus 2 times 1/2 plus 1 plus 1 over 0.4 1 minus 2 that equals minus 6.6 volts. and alpha equals 1. V out is minus 2 times 1/2 plus 1 plus 1 times 1 minus 1, it's just minus 1. So V out is less than or equal to 1 volt, or greater than or equal to 1 volt. No. V out is less than or equal to minus 1 volt. Greater than or equal to minus 6.6 volts. Now we arrange for V out. Okay, so this is the last op amp problem I have. This is a sort of modified summing op amp configuration. Normally, we would just have this positive terminal shorted to ground, and we wouldn't have this resistor here shorting us to ground here either. But overall, it's not that different. We just do KCL here. So, start off, we have these 3 voltage sources, input voltage sources. Those are given. VA is 4 volts, VB is 9 volts, VC is 13 volts, VD down here is 8 volts, which is the same as VN and VP, since we assume it's ideal. If we do KCL at this node, we'll be able to get V out. So it's just Vn minus VA over RA plus Vn minus VB over RB plus Vn minus VC over RC plus Vn minus V naught over RF, this feedback resistor here, plus Vn over Rg. Didn't name this Rg in the problem, I named it that so that I could use a variable for it. It's just the current going from here to ground. This all equals 0. I skip a couple steps here, but you can see we can pretty easily solve for V out, right? We just subtract this term from this side, from both sides. It moves over to this side. We multiply what's left on this side by RF, and then add Vn to it. So we end up with V naught equals Vn plus RF times Vn minus VA over RA plus Vn minus VB over RB plus Vn minus VC over RC and Vn over RG and everything. Yeah. Okay. We just plug into that. So 8 plus 220 times 8 minus 4 over 40 plus 8 minus 9 over 22 plus 8 minus 13 over, should be RC here, over 100 plus 8 over 352. You plug that into a calculator and you get a nice round 14 volts. Must mean that's the correct answer if it's nice and round like that. For part B, they keep all the values the same except for VA, which they're having us vary to see what the maximum and minimum values are of it. I didn't draw it in here, but this goes from 15 volts to minus 15 volts on the source. So this is still in linear. We want to figure out how much we can vary VA. So if we just go back to this, plug in every value except for VA, and then solve for VA in terms of V0, we'll be able to very easily get the range on VA. So my apologies, it's starting to get windy, so the garage doors are kind of banging a bit. Try to be quick. 8 volts plus 220 times 8 minus VA over 40 plus 8 minus 9 over 22. I switched to a different color for this one, getting a bit fun to see. 8 minus 9 over 22 plus 8 minus 13 over 100 plus 8 over 352. Okay. If we evaluate this whole piece and multiply it by that, we will get equals 8 plus 22 over 40 is 5.5. 5.5 times 8 minus VA minus 16 is this whole piece times that. Minus 16. Okay, so you can easily solve that for VA. VA is 8 minus plus 8 over 5.5. So if we just plug in V0's 15, V0 is 15, get VA is 8, and this one's dying too. Minus 15 plus 8 over 5.5, that is 3.82. 1 is negative 15. VA is 8 minus 15 plus 8 over 5.5. That is 9.28. So the final range we get is that VA is going to be greater than or equal to 3.82. 8 to, that's really terrible. Markers have been very, very unimpressive. 3.82 less than or equal to VA less than or equal to 9.28 volts. And that's your final answer. So that's the end of the video. I hope these examples were helpful for you. I'm not sure about these chalk markers. I bought them for this, but I'm not very impressed with the performance. I have to see when I'm looking back at this. I might either switch back to chalk or just break down and buy a whiteboard. If you have any questions about this, email me or reach out to me somehow. Feel free to email me to schedule office hours or ask any questions about homework or anything. And have a great week.